There we go.
Thank
okay,
you.
I can record.
Thank you.
Cool. Well, so yeah, today I'll be just giving a brief overview of computational workflows and in particular Snakemake. But starting from the start, why do we care about computational workflows? And this is really in the context of the replication crisis. So the idea that many published studies are often difficult or impossible to replicate or reproduce. And why do we care about this? Just because this can undermine our trust in scientific findings, this can slow progress, and also if we have to replicate other people's work, we can spend days, months, years trying to replicate stuff when we shouldn't have to be if it was reproducible in the first place. And on the example here is on the side here is a reproducibility project for cancer biology. And they basically aim to replicate 193 experiments from 53 papers, and basically they couldn't do this for any of them. And this was a mixture of, again, it's a bit hard to see there, but data wasn't shared, the analysis reported wasn't complete. Nearly more than 50% of studies that used code didn't share their code. So after they sort of went back to authors, clarified protocols, added the original 193, they did 87 experiments, of which 50 of them were able to be replicated. After going back to the authors, right? And so then the sort of these root causes, and more in the context of bioinformatics, is that we often have this incomplete documentation of methodologies and code. We're using non-standardized tools and computational environments. You also just have lack of access to original data and computational resources. And we saw this with Roxana's PhD supervisor over the weekend, where there was a big Twitter thread about trying to get original geosomostats.
Were they able to replicate any without reaching out to the author?
No. Zero. So zero replication. Right. And so when we're thinking about reproducible computational research, there's sort of these 5 pillars. And what sort of underbeds all this is like having this end-to-end automated process where you go from like collecting the data or downloading the data. And I'm not just talking about we go to a repository and click the download button and put it up on the Winton. That even that in itself should be programmatic, like using data get or curl to pull down the data set as part of a workflow, doing all the analysis, right to like producing the actual figures that go into a publication. And so part of these 5 pillars, and first of all, we have like this idea of order programming, where you're not just doing the analysis steps, but also integrating in explanations of why you're doing this. So this is often in the context of Jupyter notebooks, Markdown, or Cortero, for instance. We should also have code version controls. So this is like using Git to track changes as we make code and regularly pushing this onto the Git repository and using branches, particularly when we're collaborating with people. Second, we then have these compute environment controls. So different software changes over time. You've got different package versions. And particularly like using comparatory software that was built back in like 2008, that was designed to run on operating systems in 2008, so like Windows like 2000 or something, right? So if you try to run that on Windows 11 now, it may not even work. So having these fixed computational environments is also pretty critical to be able to reproduce these analysis. And then going back to data sharing, we've got these FAIR principles, so it's findable, accessible. I can't remember INR, but the idea that this data is publicly available, easily to identify, or that's what I stand for, identifying, and you can download it. And then what sort of glues all this together, of course, is documentation. So having the README, but also like commenting your code. And this also sort of fits back into this idea of order program as well. So you can sort of think about this as an iceberg, and sort of my own research is sort of taking the trajectory. So like my very first paper is basically not reproducible at all. I was using SPSS, it was all point and click, but there is no record of what I did to get those analyses. So no one here would be able to reproduce what I did based on the methods. And God forbid people who are using Excel to do analysis and generate figures. But then we can sort of go down this iceberg, or we start actually using R to write scripts. But maybe these are only stored in your machine. No one else can run them, but there's no systematic way these scripts are stored. But then I said we can go down, we can use Git, we can download Git repositories. We can start then putting some infrastructure around this code to make sure we have like frozen environments in the context of this figure. They're talking about R and the targets package, so using RM and targets. But then using tying all our scripts that we write together into a workflow with pre-specified computational environments. And there's been a whole bunch of tools that have been developed to do this. So some targets is the R package version of this. Nextflow is also fairly popular. Snakemake, which is the one we're talking about here, uses Python-based language. Cromwell, which is used by the Broad Institute, is based off a WDL language. So Snakemake sort of comes into this idea with producing sustainable research, which is underpinned by research being racked, reproducible, adaptable, and transparent. So it's not just about being reproducible. We also have to have pipelines that are being adaptable to like other projects. So I write an MR pipeline for Alzheimer's disease, but we can apply this to COVID-19. But also being transparent, so this is again having documentation, traceability, and readability, and sort of underpinning these three layers, we have like automation. So having our workflows being executable on a cluster, which also ties into scalability. So if we have a workflow that can only do one analysis at a time, that's pretty slow, right? You want to be able to spread this out so we can run more analyses in parallel. We also want them to be portable, so it doesn't just work on Winton, but we can give the same pipeline to Brian to run it now Sinai. But also being human readable, so this is where Python is nice. And then being able to trace what parameters we've used at each step and having documentation that matches that.
Although we are running into some portability issues right now.
Yeah, well,
hopefully that's not solved.
Yeah, that's less of a Snakemake issue and more of a profile issue. That have like different compute clusters having slightly different architectures. But we'll get to that at the end as well.
The take home is that we can run the stuff in a reproducible manner. It just might be very, very slow.
Yeah. And it takes a bit of learning curve to get started when you go to a new institution. So Snakemake has a recommended directory structure. And again, like having a standardized directory that everyone in the lab uses. Also, again, just facilitates research being again more reproducible and transparent, because we know like where your readme should be stored, where your workflow should be stored, where your environmental file should be stored. And again, this also just makes it easier to run these workflows. So at a high level, Snakemake consists of several things involved. First of all, you got your snake file, which is stored in your workflow directory. This is basically the central file that defines what your pipeline is trying to do. You then have a config file, which specifies like the specific analysis configuration, so like the particular parameters you're using, the particular data sets you're using, etc. You then have your environmental YAMLs, which can define your environments. And generally, these are very fine-grained, so like each rule within a workflow will have a specific environment that it runs in. We can also break down our workflow into separate snake files, which are then stored within the rules directory. So Brian often does this by having a separate Snakemake workflow that is just purely there to download data sets before you even run the main workflow. And then we also have our scripts, which are stored in the workflow scripts directory, and these are the analysis-specific scripts that you write to make a plot in R or something. There's some other folders in there we haven't really used too much, such as Jupyter Notebooks and reports. There's also a few folders that we tend to bring there, like I tend to have a data folder for intermediary outputs and also a log folder for log files. The resources folder is then really used like the data sets you download from external repositories, and then the results files in there where the outputs go. So, what does the snake file contain? At its minimum, it needs two rules. You have a rule which basically defines the final expected output of your total workflow, and then you have other intermediary rules that generate that final output. So here we're saying that the very final thing that we have being produced by this workflow is a file called sample.txt. And that sample.txt is produced by the next rule, quantify genes. So these rules then, again, like at a bare minimum, have three directories: your inputs, your outputs, and then whatever your command is. So here we're saying that we have three files: FASTA file or a genome reference, two sample files, and basically we expect the output of this to be our sample.txt file, and then our shell command is basically just echoing these three file names together. So this is the basic core of a workflow. And then when this gets more complicated, you start writing more and more rules that go through this whole pipeline. Is there any questions there? Yep, there is a chat question. Is this like a template? I've written a sandbox snake file, Stephanie, that I've used for doing this, which you can see up on GitHub. I'll have the read the docs at the end of the presentation, and that has like a much more complex tutorial. But yeah, basically input, output, and either a shell run or a script file. Like those are the three main directives. Yeah. Okay.
Can I just ask something?
Yeah.
You know when it says echo, all it does is kind of say what the file name is.
Yeah.
And
Yes. So
I
this
mean,
is just my example.
Okay.
Yeah. I mean, for instance, you could have like a link command there, or you could have like GenoTools for Caroline's work.
This is actually sometimes useful in practice because unless you go into some of the more advanced usage of Snakemake, it only calculates the graph for what it's going to do once at the beginning. So if there are things that depend on the files that are created, you may need to basically generate intermediate configuration files in order to run future steps. So this is like obviously for the demonstration, but you may end up using things like this in real life.
Yeah. Yeah, and I should say in the shell command there, we're basically calling on the inputs and the outputs from the Snakemake rule. So we're saying echo input genome, input R1, input R2, which corresponds to the input directives and the output directives. You notice that for the output here, I don't say like output.R1 or something like that. That's basically saying all the output files in the output directive. So if I had multiple output files, I was expecting I could say output 1, output 2, for instance. Okay, so this is making one file called sample.txt. But what if we want to do more than one sample? And this is where Snake makes us become more powerful, where we start introducing wildcards. And the idea here is to start generalizing what our expected inputs and outputs are. So here we're basically saying at the top, we are having what's called, basically saying we have two sets of files called sample1 and sample2. And we want to basically run this pipeline on that whole lot of both those samples at the same time. And so what we're doing then is we, again, we have a rule all, we're saying we expect a final output.txt now. And in our next rule, quantify genes, rather than saying sample1.r1, we're putting in what our wildcard is, which is called sample. So then Snakemake will basically say, replace that sample wildcard with sample1 and sample2, and this will propagate through every other rule. What Snakemake then expects is defining what sample is. So either you can do this in the rule all, for instance, but here, because what my second rule is that it's basically colliding both of those outputs. So from the previous rule into one final text. In the input here, we're saying sample equals samples, and samples is defined at the start of the pipeline. So then this basically propagates back to every other rule that depends on this collect outputs rule. And you can see here, rather than using the shell command, I'm now using a run. Go back. I want to do that now. No. Yeah, but you guys can't see my mouse.
We can see your mouse.
Yeah, I was trying to get the latest one. Yeah, so basically, rather than using the shell command, I'm now using the run command. And this is basically running a bunch of Python code that basically appends these two files together. And again, we'll show how this changes later on. But basically, the idea is, these wildcards then are starting to make our workflows more adaptable to different analyses. And basically, what we can do then is basically visualize this. There's some chats there. Oh yeah, and then Brian said we can use inputs, outputs, and wildcards with every single run within different shells and scripts. So basically, on the right here, we then have a DAG, basically showing what our workflow looks like. So we have our first rule, quantify genes, which flows into our collate outputs, that goes into our final rule. And this is called a rule graph. And we can now expand this out into a DAG, which shows what's been done across all our different inputs. So we're saying we have quantifying genes being run on sample 1 and sample 2, which feeds into collate outputs that goes into our final rule. So Caroline, at the start, or in the rule collate outputs, we're basically saying the sample wildcard reflects samples which we've defined at the top here with the config.
It can run into issues. So basically what Snakemake will do when it's generating the DAG is it will start from the final rule, so the rule all or whatever file you ask for, and then look for all the rules that can create the files needed for that, and then looks for all the rules that create the files needed for the rules, the previous rule, etc. And if you have more than one rule that might be able to generate the thing, it can get confused. And there's various ways that you can fix that if you run into the issue. But so it basically traces the whole thing back from the end to the first file. And if it's missing anything, it will let you know. If there's more than one rule that can create it, it will let you know. So it's pretty obvious what's going on if something has broken for that.
Yeah, they do generally recommend when you're defining what your outputs are, that they should actually be going into another directory that's labeled with your rule. So it'll be like data, quantify genes, and all your quantify gene outputs will go into that directory. Then you have another directory for collate outputs. That sort of breaks those naming issues that Brian was describing.
And I do not do that, unfortunately.
Yeah, I've started to do it a little bit more. Okay, so in addition to defining inputs and outputs, we can also define parameters. So these are basically tend to be like static specifications for different commands. So for instance, if we're using admixture and we wanted to define the number of Ks we wanted to use, we could have a parameter there called K that then gets fed into our shell command. So the example here is that we have a parameter for genome build, so we're saying build 38. And again, within the shell command, we can basically say we want to use this specific parameter. So if we're using link again, for instance, we could define different arguments within the link run command, within the parameters. We can also technically make parameters wildcards as well. Again, so long as those parameters are then defined in the input and outputs as well. So that can be useful again, like if you want to run stuff across build 37 and build 38, we could adjust our file names to be like sample as one wildcard and then build to be another wildcard. And basically then we'll be doubling the number of analyses we're running again in parallel.
Snakemake will also track what parameters were used to generate an output, and if the parameters change, it will rerun the thing. So you can have a thing that's not actually in the file name, but it will rerun it if it's changed.
And so before, I was basically using samples defined within the main Snakemake workflow. But again, this is basically hard coding what we expect samples to be, right? Within the workflow system where we can use these configuration files. So these are stored within the config directory, and basically either use a JSON or a YAML format. There's also an option to use TSVs as well, which we haven't used so much. But basically we have a second file where we're defining what the samples are, so sample 1 and 2, and what the build is, build 38. And then within the Snakemake, we're basically we're using the config file directive to call upon that specific config file. And then we're saying, from the config file, call in the samples, put that into a dictionary called samples, which then gets fed into the Snakemake workflows. You can see again for the parameters too, we're saying here from the config file, take the build parameter and run that into our shell command. So again, this just makes your work more adaptable, so we can basically have multiple config files for different types of analysis that we want to run. So again, when I've been using MR pipelines, I did one with APOE and one without, and one of my parameters within that config file was within the APOE region. So earlier we saw for the collate outputs, we basically had a run command where we had all our Python code within that run command. Again, this can get hard to debug because if you have multiple rules with multiple Python functions in it, it just gets hard to debug. Your workflows become much longer. It becomes harder to test. So again, it's just good practice to break out every script you run or every command you're running into a separate script. So here, rather than using shell or run, we have a scripts directive that's pointing towards our scripts directory in the new Python file we call collate outputs.py. And we then have that Python command there. So how does the scripts file know what to run? Basically, Snakemake has environmental variables. So we can basically call within their Python script to say we want to use snakemake.input, so we'll read in all our input files. And we can say for our output files, we use Snakemake output. And then you can further break that down by saying we want to use, for instance, the first item within the output by defining 0 here, because Python is 0 based and not 1 based. We could also do this with snakemake.input. We could say we want to have 2 different input files and specify those specifically. But the way we read our Python command, we don't need to do this here. So again, this is really making your workflow much more modular, much more portable across different environments. And again, we can link these script files within a particular kind of environment. So we're having a specific computational environment for that specific field. And again, like these scripts are fairly flexible, so they can be, an R script, a Python script, or even a shell script. Yes, Rust is probably supported, Brian. I've never used it, same with Julia. Apparently, they're much faster than using R or Python. So yeah, maybe that's what you guys should be learning and leaving us old dogs behind.
Open admixture is programmed in Julia. So
yeah, and then talking about environments. So Snakemake can use either conda environments, or it can also use Docker in combination with Singularity. But basically within our environments directory, we're defining, again, another environmental YAML, which basically is composed of a name, channels where we want to download our packages from. So here we're just using the defaults defined by Snakemake when we install Snakemake, but we could say we only want to use like Conda Forge, for instance, or Anaconda. And here we're saying we want to make an environment that's solely composed of Python version 3.8. So every time we run this rule now, it will always be ran within an environment that has Python 3.8 installed. And we basically say, again, within our Snakemake rule, we have a conda directory pointing towards the specific conda environment that we want to use. So this is where Snakemake can start to become a bit slow. And also why they recommend installing Snakemake using Mamba rather than Conda, because Mamba is much faster for building these conda environments. Again, this is getting back to that second principle we saw in those reproducible computational pillars about having very specific environments that are ran for your analysis. Right? So that way, if our packages and versions change, as software is developed, we're always using the same version that we originally ran in that pipeline. So this is all great if you want to run your analysis on your local machine, or even if you're running on Winton but not running it, taking advantage of the compute resources. So this is where we start to introduce some additional directives such as threads, which is defining the number of cores that we want to use on Winton. And also we can then specify, for instance, how much memory we want each rule to have, as well as the amount of time. And this has started where Brian and I were running into issues of getting Snakemake working on Winton, as we'll see in the next slide, where we have to basically have another set of config files that define the compute cluster that we're using. But basically, this starts to allow us to be more specific in what compute resources we're requesting in every rule. So we don't have to have like an overall saying we want to have 20 cores with 10 gigs each. We can say again have a very fine detail of the amount of resources we want per rule. Again, this will help us with job submission and getting our jobs to move faster. And so when we want to run on the cluster, we basically have to define, or we don't have to define a profile. You can do this on the command line, but it's much more efficient to define a specific profile. And these are basically pre-configured sets of options that are tailored for our specific cluster environment. And basically other smart people have written these profiles. So there's like an SGE profile that I was using on Winton, but some of these predefined config sets actually didn't match what Winton uses, even though it's SGE. So Brian, so in particular, like the memory usage and the time usage is not really compatible with other like LSF, which is what Brian was using. Also, the way Winton defines the number of cores that are used is through parallel environments rather than actually defining the number of slots. So we've had to define, as we go back and change these profiles to work on Winton. Which, luckily for everybody here, I've now put up on GitHub. So basically, you can just clone this into your home directory, and it should run. So you can let us know if it doesn't run and have any problems. But basically, you can see here, there's basically a number of files that basically involve submitting the jobs, checking the status of what the job is, and then canceling if you need to cancel it. And then the cluster YAML can be used to define defaults for the cluster submission. So basically here we're saying our default for the parallel environment is SMP, but we could also change that to MPI if we want to. And also defining where the output of our log files go as well. So hopefully, so like the last week and a half where I've been paying back in Snakemake working on Winton, it's literally been because of this. So hopefully that should make things a lot easier. So then the final thing I'll talk about today then is modules. So the idea here is that we can have core pipelines that everybody can use. For instance, we might have a GWAS QC pipeline, and rather than basically copying this workflow every time we want to QC in a GWAS dataset, we can have a master pipeline that we basically call upon. So this is where we have like our Snakemake workflow in another directory or even on GitHub that's called GWAS QC. And we can basically call upon this workflow, for instance, either using GitHub or if it's still in our local machine, we can basically point towards that directory. And basically within our specific GWAS data set, we can say, for this data set, we want to use this workflow, but then maybe there's some other downstream rules that we need to modify. So we can basically say maybe some of our parameters are wrong. So maybe it's the default for our original workflow is in build 38, but this data set's in build 37. So we can basically go through and start changing some of those parameters for specific rules in this workflow that we're calling on as a module. So again, like this again makes our original workflows much more portable. So Brian's got his GWAS QC pipeline that we've written together. We can now basically use the same pipeline here at ECSF. So again, this just makes them more accessible, more portable, more usable. There's also an alternative called include. So when I was saying earlier, Brian often writes a sub workflow for downloading datasets. We often use an include rather than a module. That's because that workflow is within the specific analysis directory. So just some examples of how I've used Snakemake. So a lot of you have seen this jet architecture of AD figure. Firstly, looking at the allele frequency by the effect size across all the major European ancestry geologists. This was written in Snakemake, and this is the DAG that we have for this. So this is an example where this is probably not super adaptable to other analyses because this was written very specifically, but basically here, because the Lingay and Janssen didn't make their most recent GWAS summary stats publicly available, I got the PDFs, versions of their main hits from each paper and read those into R and munged them in R to get them to a TSV format. Right, so again, like having these data sets, like even that very simple munging step was done in R and is reproducible. Even though necessarily downloading the PDFs was reproducible because I had to do that. And then, but after that sort of munging step, which is specific to each data set, everything after that is probably actually adaptable to another analysis, where we're going through like defining loci based on LD clumping and how close each lib snip is to each other, annotating it with effect sizes, and actually I think this was using SnipF, so that was predictive functions of variance, renaming things with DB SNP RSIDs, merging loci together, identifying what the cytobands are, getting allele frequencies from MONAD, right? And then going down to actually making that figure, which is a specific script. Similar, this is from my MR paper. So this is an example of where if I did each of these pairs of analyses in an individual script file, I would have killed myself. Because this is like 430 separate analyses. Like you can't do this. Like Andrea's already running this problem with like 3 different data sets where she's written the script file for each MR analysis. This starts to just become unwieldy, particularly if you go through like changing different parameters in different analyses. Then you have to go back and change all those in each individual script file. So this is where, again, Snakemake becomes powerful because you can have this generalizable workflow where you can have multiple inputs coming out with outputs at the end. They're all going through exactly the same analytical steps. Particularly, again, like if you're copying and pasting code, that's easy to copy and paste mistakes, not fix mistakes in other analyses. And this is just the example of what that workflow looked like. Again, this is very small to read, but we're going like, formatting our exposure data sets, plunging them, formatting our outcomes, harmonizing those data sets, putting them through various MR analyses, removing outliers, generating HTML reports, and then all that sort of goes into our final report. And so this is really just to highlight that, here we're specifically using Snakemake, but Nextflow, Cromwell, all these computational workflows basically underpin developing robust and reproducible scientific analyses, right? So they're sustainable because they're reproducible, they're adaptable, and they're transparent. This also allows us to do more analysis, right? I mean, if we have these computational workflows, we actually start thinking about doing things wide. We don't have to reinvent the wheel every time we want to QC another genotyping data set. It saves time, makes things more reproducible. And we can collaborate and reuse pipelines. So Brian and I are still working on pipelines together because that's what we're going to do. I don't want to have to reinvent a GWAS QC pipeline. That's a lot of work that we put into that one, and I don't want to do it again. And these are just some resources, a few pages I mentioned at the start. So the Rodriguez one there, that's a book they wrote specifically for using targets in R. You got those 5 pillars of computational research. The Mulder paper sort of outlined why they're using Snakemake. And of course, look at Snakemake, read the docs. I've only touched on some of the things that Snakemake can do, like these are like the core competencies that you need for developing a workflow, but it can do a lot more than that. Eventually, I'll go through and fill in some more of this information in the lab handbook. And that example workflow is what I was going through, that's available on Git. This is basically just a test example, like you use to debug different Snakemake options, for instance.